Transformation of charge and current densities. Current 4 vector. In Minkowski space, which is 4-dimensional space, current density J and charge density rho are grouped together to form current 4 vector J mu, as J mu equal to J vector and IC rho. There are 4 components of this current 4 vector. 3 components are components of J vector, current density, Jx, Jy and Jz, and 4th component is related with charge density rho, and 4th component is IC rho. So 3 components of current density J vector and rho, charge density multiplied by IC. These 4 components form a 4 vector that is known as current 4 vector. If we consider a volume element d tau equal to dx1, dx2, dx3, dx dy dz, if rho is charge density, then charge contained in this volume element will be equal to dq equal to rho dx1, dx2, dx3. It is from the definition of charge density rho, which is equal to charge upon volume. So charge is equal to charge density rho into volume. So charge dq inside volume element dx1, dx2, dx3 will be equal to rho into dx1, dx2, dx3. If we multiply this equation by a 4 vector dx mu, x mu is position 4 vector, we get dq into dx mu equal to rho dx1, dx2, dx3 into dx mu equal to rho dx mu upon dt, dx1, dx2, dx3 into dt, multiplying and dividing by dt. As charge is invariant, left hand side of above equation is a 4 vector. In left hand side we have dq into dx mu. Dx mu is a 4 vector and charge dq is invariant. So left hand side of this equation is a 4 vector. So right hand side of this equation must be a 4 vector. Further, we know that 4-dimensional volume element is Lorentz invariant. dx1, dx2, dx3, dx4 is 4-dimensional volume element which is invariant. Here x4 is ICT. So dx1, dx2, dx3 into dt is invariant. So in right hand side of equation 2, left hand side is a 4 vector which is Lorentz invariant. in right hand side dx1, dx2, dx3 into dt is Lorentz invariant. So the remaining term in the right hand side, which is rho dx mu upon dt, this must be a 4 vector. And this 4 vector is current 4 vector, which we write as J mu. So current 4 vector J mu is written as rho into dx mu upon dt. Its first component J1 is rho dx1 upon dt. dx1 upon dt is dx upon dt, x component of velocity, which we write as u1. So J1 is equal to rho u1. Similarly, J2 is equal to rho u2 and J3 is equal to rho u3. Fourth component of this current 4 vector J4 is equal to rho dx4 upon dt. x4 is ICT, so it becomes equal to IC rho. So current 4 vector J mu is equal to J vector and IC rho. First three components are components of J vector J1, J2, J3, which are equal to rho u1, rho u2, rho u3. Rho multiplied by velocity, it represent current density. Now J mu is current 4 vector, so it must transform under Lorentz transformation as J mu dash equal to alpha mu nu J nu. J mu dash is a column matrix, J1 dash, J2 dash, J3 dash, J4 dash. Alpha mu nu is this square matrix and J nu is again a column matrix, J1, J2, J3 and J4. This equation shows how current 4 vector transform under Lorentz transformation. J nu are components in S frame, which is at rest, and J mu dash are components in moving frame S dash. From this equation we can write 4 equations which relates J1 dash, J2 dash, J3 dash and J4 dash to J1, J2, J3 and J4. These are 4 equations. J1 dash equal to gamma J1 plus I gamma beta J4. Gamma is common, gamma into J1 plus I beta J4, gamma into J1 plus I, substitute V upon C for beta, and IC rho for J4. Then J1 dash becomes equal to gamma J1 minus V rho. Similarly, other equations are J2 dash equal to J2, J3 dash equal to J3 and J4 dash equal to minus I gamma beta J1 plus gamma J4. Gamma is common, gamma into J4 minus I beta J1. Now J4 dash is equal to IC rho dash and J4 is equal to IC rho. Substituting these values, this equation reduces to this equation. I c rho dash equal to gamma I c rho minus I v upon c j1. Dividing by IC, we find the relation between rho dash and rho. Rho dash is given as equal to gamma rho minus V upon C square J1. These are the transformation equations for current and charge densities. So current for vector J mu is rho dx mu upon dt. Four components of this current for vector are J vector and IC rho, and these are the transformation equations for charge and current densities under Lorentz transformation. Next topic is electromagnetic vector and scalar potentials. In a region of charge density rho and current density J vector, Maxwell's field equations are. There are four Maxwell's equations. First is del dot E equal to rho upon epsilon 0. Second is del dot B equal to 0. Third is del cross E equal to minus delta B upon delta T. And fourth is del cross B equal to mu 0 into J plus epsilon 0 delta E upon delta T. Here E vector is electric field vector and B vector is magnetic field vector. Epsilon 0 and mu 0 are permittivity and permeability of free space. Epsilon 0 is permittivity and mu 0 is permeability of free space. In a dielectric medium, we use epsilon and mu for permittivity and permeability. For free space or vacuum, we will use the index 0, epsilon 0 and mu 0. These are permittivity and permeability for free space. As divergence of curl of any vector A is always 0, that is del dot del cross A is always 0. Del cross A is curl A and del dot means divergence. So divergence of curl A is 0. Del dot del cross A is equal to 0. From equation 2, second Maxwell equation, B vector can be expressed as the curl of any vector A. Second equation, second Maxwell equation is del dot B is 0 and del dot del cross A is always 0. So we can write B vector as del cross A. Here A vector is known as electromagnetic vector potential. Substituting the value of B vector from above equation in equation 3 in third Maxwell's equations, we get del cross E equal to minus delta B upon delta T and substitute B equal to del cross A. So this Maxwell equation reduces to this equation. Del cross E equal to minus delta upon delta T del cross A, which is equal to del cross minus delta A upon delta T. del cross is taken outside. Remaining term is minus delta A upon delta T. So del cross is taken common. We bring right hand side to left hand side. So this equation becomes del cross E plus delta A upon delta T equal to 0. As curl of gradient of any scalar phi is always 0, that is del cross del phi is equal to 0. So from this equation, del cross E plus delta A upon delta T equal to 0 and del cross del phi equal to 0. We can write the bracket term E plus delta A upon delta T as gradient of scalar potential phi, and we write it as equal to minus del phi. So E plus delta A upon delta T is equal to minus del phi, or E vector now becomes equal to minus del phi minus delta A upon delta T. Scalar phi is known as electromagnetic scalar potential. Substituting the values of B vector and A vector from equations 5 and 7 in equation 4 is fourth Maxwell's equation, we get del cross A equal to mu 0 J plus mu 0 epsilon 0 delta upon delta T minus del phi minus delta A upon delta T. Del cross A is equal to del of del dot A minus del dot del A. Del dot del is del square. Here we have used the formula of A vector cross B vector cross C vector. A vector cross B vector cross C vector is equal to A dot C times B minus A dot B times C. So left hand side, which is del cross A, becomes del of del dot A minus del square A, and right hand side is mu 0 J plus mu 0 epsilon 0 delta upon delta T minus del phi minus mu 0 epsilon 0 d2A upon dt square. Delta upon delta T is operated on del phi and delta upon delta T is operated on delta A upon delta T. Now this equation becomes del square A minus mu 0 epsilon 0 d2A upon dt square minus del of del dot A plus mu 0 epsilon 0 delta phi upon delta T. Del vector is taken common in two terms. And this becomes equal to minus mu 0 J. Similarly, substituting the value of E vector from equation 7 in equation 1, we get del dot minus del phi minus delta A upon delta T equal to rho upon epsilon 0. This equation reduces to minus del dot del phi minus delta upon delta T del dot A and this term mu 0 epsilon 0 d2 phi upon dt square is added and subtracted and it equal to rho upon epsilon 0. So this equation becomes del square phi minus mu 0 epsilon 0 d2 phi upon dt square plus delta upon delta t del dot A plus mu 0 epsilon 0 delta phi upon delta t equal to minus rho upon epsilon 0. Equations 8 and 9 represent two inhomogeneous wave equations in terms of electromagnetic vector and scalar potentials A and phi. A is electromagnetic vector potential and phi is electromagnetic scalar potential. These inhomogeneous wave equations can be uncoupled by using concept that A vector and phi are arbitrary. Generally, A and phi are chosen subject to the condition del dot A plus mu 0 epsilon 0 delta phi upon delta t equal to 0. This is the term which appears in these equations. Equation 9, this bracket term del dot A plus mu 0 epsilon 0 delta phi upon delta t, and also in this equation 8, this bracket term del dot A plus mu 0 epsilon 0 delta phi upon delta t. This term appears both in equation 8 and 9 inside the bracket. If A vector and phi, vector potential and scalar potential, these are chosen subject to this condition that this term becomes 0. This condition is known as Lorentz condition. Equations 8 and 9 then becomes del square A minus mu 0 epsilon 0 d2A upon dt square equal to minus mu 0 j, and del square phi minus mu 0 epsilon 0 d2 phi upon dt square equal to minus rho upon epsilon 0. Equations 10, 11 and 12 form a set of equations equivalent in all respect to Maxwell's equations. This Lorentz condition and these two equations of A vector and phi, these equations are equivalent to 4 Maxwell's equations. As speed of light in vacuum c is equal to 1 upon under root mu 0 epsilon 0, so mu 0 epsilon 0 is equal to 1 upon c square. Equations 11 and 12 then becomes del square A minus 1 upon c square d2A upon dt square equal to minus mu 0 j, and del square phi minus 1 upon c square d2 phi upon dt square equal to minus rho upon epsilon 0. These equations can be written as del square A equal to minus mu 0 j and del square phi equal to minus rho upon epsilon 0. Here del square is D'Alembertian which is equal to this del square minus 1 upon c square d2 by dt square. In left hand side, except a, the remaining term is this D'Alembertian del square, and this equation becomes equal to this equation. In short, D'Alembertian del square a equal to minus mu 0 j and del square phi equal to minus rho upon epsilon 0. So these are the wave equations for electromagnetic vector potential A and scalar potential phi, and this is the Lorentz condition: del dot A plus mu 0 epsilon 0 delta phi upon delta t equal to 0.